In this video, we're going to do a slightly more complicated double integral of a function over a region where this region D is a circular region. The more difficult parts of the double integral, or the part of the double integral that makes evaluating these integrals rather more difficult, is the particular region D. So in this case, this is problem number 46. Number 46, so that's section 14.2, number 46. Okay, and in this problem they ask you to find the volume of the region bounded by the cylinder. The cylinder they've given us is x squared plus y squared is equal to 4. So they've given us the implicit form of the cylinder, and they want us to find a region by bounding it by two planes. And the two planes, z is equal to 4 minus y, and z is equal to 0. So if I was to kind of just look at a little rough sketch here, I would say that we have some sort of cylinder. Here's the z equals 0 plane. There's z equals 0. And there must be some other plane coming through here, cutting this cylinder into a circle. Right? And so the volume that we're looking for is the volume of this region. And that's what we want to find. Okay. So we need to set up a double integral for this. Okay. We want to find the volume below this surface, but above the z equals 0 plane. So this surface is our plane, right? So we've utilized one of the pieces of data to find the function we actually need to integrate. Then our region D that we are trying to integrate over is this region down here given by the circle. D is given by the circle, which is the circle x squared plus y squared is equal to 4. So the cylinder itself is setting the outer bound, so the cylinder is setting the domain D. And so for any z, we are getting a circle. This cylinder is a circle for any value of z. So for the particular value z equals 0, we have a circle. So our region D that we are looking at is the circular region in the xy plane. And to describe this as a function, the top half, y would be the positive square root of 4 minus x squared. And the bottom half of this circle, to describe it as a function, is y is equal to negative square root 4 minus x squared. Okay. So if we wanted to tackle this integral as a dy dx problem, it would be pretty straightforward to set this up as y is equal to the bottom limit, the bottom edge of the circle, negative square root of 4 minus x squared, up to y is equal to positive square root of 4 minus x squared. And x goes from negative 2 to 2. Pen's not quite behaving today. Negative 2 to 2. Okay. So there is the integral that we would need to evaluate. Okay. So if you are actually step 1, oftentimes they could just say set up the integral, and then you would be done. But this problem has asked us to find the volume, so step 2 is to actually evaluate the integral. Right? So we need to try to tackle this integral, and as I've said what makes this problem rather difficult is that this region D is a circle, and that causes us problems when we try to describe that circle in terms of functions of x. Therefore, we're introducing these square roots into the problem, and it looks like that could cause us some difficulty. And let's see what sort of difficulty that causes us. So we would do this as an iterated integral. 14.2 is about iterated integrals. All right, so let's do this as a dy problem first. And so I would integrate from negative square root 4 minus x squared up to the square root of 4 minus x squared. And I need to integrate 4 minus y dy. Okay. So pretty straightforward to integrate this function. This function itself is not causing us problems. That is easy to integrate as 4y minus y squared over 2. And then we need to evaluate from negative square root 4 minus x squared to square root 4 minus x squared, which gives us 4 square root 4 minus x squared minus 4 minus x squared divided by 2. The squared and the square root cancel. There's the top limit. And then I need to subtract out the bottom limit, which would be negative 4 square root 4 minus x squared. Squaring the negative square root of 4 minus x squared gives a positive, so this would still be minus 4 minus x squared over 2. Okay. And combining these two terms, we see that the 4 minus x squared terms cancel each other out, and I'm left with 8 square root of 4 minus x squared. Okay. And that would be the first double integral. Probably a good idea at this point to just double check this answer in Mathematica, just so you can make sure that you've progressed through this problem okay before you move on to the next step. So if I was going to test this problem, I would integrate 4 minus y, and then 4 minus y, and then y would go from negative square root 4 minus x squared up to the square root of 4 minus x squared. You can ask Mathematica to integrate that for you, and you get 8 square root of 4 minus x squared. And you're feeling pretty good about your first step. Okay, so let's get Mathematica out of the way. Bring back the problem to finish the iterated integral. Okay. So we need to continue. We need to do the integral from negative 2 to 2 of 8 square root of 4 minus x squared. And here is where the square root description of the circle is going to come back to not haunt us, but cause us trouble. We now have to evaluate this integral with the square root in it. If you'll recall from Calculus 2 that this is a trig substitution. And for example, you could let x squared is equal to 4 sine squared of theta. That would be that x is equal to 2 sine of theta. And then dx is equal to 2, derivative of sine of theta is cosine of theta d theta. So if you're going to make the substitution here, I would do 8 square root 4 minus x squared, that would be 4 minus 4 sine squared of theta. And then dx is equal to 2 cosine of theta d theta. So I see where this is going. We're going to have theta limits here. When theta is -2, x is equal to, when x is equal to -2, when x is equal to -2, we need to solve for theta. Okay, so that would be -1 is equal to sine of theta. Okay. And the other limit would be 2 is equal to 2 sine of theta, trying to find my theta limits. So when is the sine of theta -1? That would be at -pi/2. And when is the sine of theta 1? That would be at theta is equal to pi/2. Still have a little bit of work to do here. We're now going to go from -pi/2 to pi/2. The 4 factors out and comes out of the square root as a 2, so that would be 16. 16 times 2 is 32. And then I get the square root of 1 minus sine squared. And then I have this cosine of theta here, d theta. Okay. -pi/2 to pi/2. 32. Square root of 1 minus sine squared. 1 minus sine squared, according to one of the Pythagorean identities, is cosine squared. Square root of cosine squared is cosine. So now we're down to cosine squared of theta d theta. And then I'm pretty sure that there is a trig identity. A trig identity for cosine squared, probably one of the double angle formulas. And how do I remember that? Cosine squared of theta. Well, we could do an internet search for that, or I could derive it. I could derive this from sine squared theta plus cosine squared theta is equal to 1. So cosine squared theta is equal to 1 minus sine squared theta. I know that and then I know some of the sum and difference formulas for sine and cosine, so I know that like sine of 2 theta is 2 cosine theta sine theta. And then cosine of 2 theta, how does this one work, is 1 minus cosine squared theta over 2, if I remember it correctly. I think this, okay, let's see if, trying to do this all the way out without resorting to any technology. But this is a formula you could look up, or I could go through the derivation of the cosine squared theta. I'm pretty sure that that is something like, according to this formula, rearrange this for cosine squared. I think you'll get like cosine of 2 theta minus 1 or something equal to cosine of 2 theta. I don't have that one memorized. So let's see if Mathematica has anything to say about that, or just, actually we'll just resort to a Google search. Resort to a Google search. Cosine squared of theta identity. Cosine squared of x identity. double angle identity. Double angle formulas. This one would actually respond. Trig identity is fine. Let's take a look. Anything here that helps us out? Yeah, right here. Cosine squared theta is 1 plus cosine 2 theta divided by 2. Cosine squared theta is 1/2 plus cosine of 2 theta over 2. So, what I say, 1/2, 1 plus cosine of 2 theta. That's cosine squared theta. Okay. So you could use that in here and then split this integral into 2 pieces. The reason I'm doing this is to show you the difficulties that can happen when you try to work with circles as your region and you try to describe them in terms of Cartesian coordinates or the XY coordinates. Okay, and now you can see that this should split into 32 divided by 2 theta. This splits into 32 divided by 2. I'm finding the antiderivative. The derivative sign is cosine. So this would be 1 sine of 2 theta divided by 2. And then I need to evaluate that from negative pi over 2 to pi over 2. And it should be a straightforward substitution at that point to just plug and chug. So if you want to figure out what that answer is going to be, double check your answer with Mathematica. Okay. I would integrate 32 times cosine of, we'll just call it x squared, and let's integrate from x from negative pi divided by 2 to pi divided by 2. And the answer comes out to be, after you would plug and chug, would come out to be 16 pi. So, hopefully we've done that problem correctly. The difficulty here was working out, okay, let's take a look here, 16 pi, and that was the volume of this region. Okay, be interesting to double check that this answer makes sense as 16 pi. So maybe we could get a look at the plot of this region. Okay, and we could even actually check our answer all the way from the very beginning. Let's just see what Mathematica has to say about plotting this region and checking the double integral from the very beginning. Let's see what it has to say about this problem. So remember, you could bring up your palette, your writing assistant. There are your integrals. I could bring in one integral, and for this center function, bring in another integral. And let's put this as the integrand, the function we are integrating, as 4 minus y. Oh, this is the wrong kind of integral. I needed a definite integral, so I didn't see any boxes on the integral. So let's go to writing assistant again. Let's insert the integral here with the bounds on the integral. Okay. And now we can fill in all the spots. This would be 4 minus y. This would be negative square root 4 minus x squared. The top bound would be the square root of 4 minus x squared. That would be a dy problem. And the last integral will be -2 to 2. -2 to 2 of a dx problem. And let's hope that when we hit Shift Enter here, we get 16 pi, and we do. So the computer has double checked that for us, which means that we did all the steps here correct, which is not bad on a first pass. Okay, so let's check that this plot, let's make sure we can plot this region, make sure you know how to plot the region. That would be a region plot 3D. We need to describe the region as z greater than 0 and z is less than the plane. The plane was 4 minus y. And we need to describe our region D here down in the xy plane. Now we've described the z region, so if we describe the xy region, that would be y is bigger than negative square root 4 minus x squared. And it is less than the square root. Square root 4 minus x squared. And then let's give that a region to plot. Let's plot this, say, from the x going from, say, -2 to 2. Y from -2 to 2. And then we want to plot it in the cube, -2 to 2, -2 to 2. And let's let z go from, say, 0 to, say, 5. And plot this region plot. And I think we can see here what we were looking at. I plot here, here is the z equals 0 plane on the bottom. Here is the plane 4 minus y. And we were looking at the region above the circle from -2 to 2. So here is our region. Right? Maybe make y go a little taller. It's been cut off here at the top, so maybe you can go to, say, 7. Okay, now we've got the whole region, and it's kind of rounded on the edges, so if you ask the computer to plot more points, you could say plot points 50. Should kind of make this a little bit more crisp. So there is a full problem which shows the double integral for a volume over a region which is a circle. And we have described the circle in terms of Cartesian coordinates, which means that we have described the top half and the bottom half of the circle as a function of x. Or you could have described this as a function of y if you wanted to integrate in the other direction, dx, dy. But in either case, you would have run into a trig substitution. You would have had to remember a double angle identity to do the cosine squared integral. But at the end of the day, you will get to the correct answer of the volume is 16 pi. In the next video, we'll talk about how to do these double integrals over circles and polar coordinates, which will be a much snappier and more straightforward way to compute the double integral.